want to. It's, again, no one loves that section. So everyone loves this section. So let's talk about finishing up some isotonicity stuff. This is a great section. I love this. You hopefully last week got some good background stuff. We talked about freezing point depression. We kind of introduced the sodium chloride equivalent method. I think you have some good basis for that. And we're going to go further and actually do the prescriptions for isotonic solutions here. But let's review that because it is important to make sure that you understand a little bit of what we talked about last time. So let's start with the review question with mannitol. It says, what is the tonicity? So here we're evaluating the tonicity of a current solution, of a 0.2 molar mannitol solution with a molecular weight of 182 and an E value of 0.18. I'll remind you, mannitol is a sugar. It's a non-electrolyte. So what is the tonicity of that solution relative to body fluids? Is it isotonic, hypotonic, or hypertonic? So we want to evaluate the tonicity, and we're going to do the same thing in two different ways. We're going to do it first with the freezing point depression method, and then we'll use the sodium chloride equivalent method. Remember, you have to be good with both of those systems. Okay? So let's think about the concentration. We were given the concentration as 0.2 molar. What does that mean? 0.2 moles per liter. Actually, if you remember back to the freezing point depression, with really both of these methods, we actually need to know the amount of drug, in this case, by its weight. So the first thing let's do is let's convert that concentration, and you'll see why here in a minute if you don't remember why, from the current expression of 0.2 molar, and let's convert that to grams per liter, because that's the number we're going to have to use, or the concentration we're going to have to use in some of our formulas. So the first step is pretty straightforward. We have 0.2 moles per liter. So let's just convert the units. We're already in liter. Good. We just need to convert back from moles to grams. And we convert moles to grams by multiplying by the molecular weight of the mannitol, which is 182 grams per mole. That way my moles cancel. I'm trying a little red here, so that cancels. And we're in grams. So this is kind of important. So is everyone okay that really 0.2 molar is the same as, we're just re-expressing the concentration as 36.4 grams per liter. So now we're in weight per liter instead of number of molecules. Okay? The reason we need to do that is if you remember back to the formula for the freezing point depression method, we said you can determine the freezing point depression of any concentration of a solution by setting it up first with, on the left-hand side, on the numerator, the molecular weight of the product, mannitol in this case, which is 182, in the units of grams per liter. And that was specific. That's why we had to get back to those units. So let's put 182, the molecular weight of mannitol, in grams per liter on the numerator. Set that over, it's essentially its freezing point depression, which we defined as negative 1.86 times its I, or its dissociation factor. And you remember we said for a non-electrolyte, since it doesn't fall apart, it doesn't produce multiple particles, its I value is 1. So negative 1.86 times 1. That's the proportion of, again, the concentration over the freezing point depression in general. Set that equal to the concentration we do have. So again, this is what we just determined. So I'm going to pull over my actual concentration, set it in there, and set it over X, and X will be the degrees, the depression, the lowering of the freezing point that occurs with that concentration of mannitol. Solve for X, take 34.6 times negative 1.86, divide that by 182. You get a final value of negative 0.37 degrees Celsius. Everyone okay for that? Does that formula look a little familiar? And again, this is a little bit of a review. Now, this is kind of an important idea, and we're going to go forward with this. In the freezing point depression method, now the idea is we've got to compare our solution here to a normal biologic fluid. What was the freezing point of an isotonic solution? Body fluids freeze at what? This is what you got to memorize, negative 0.52. That's the value that would be isotonic with biologic fluids. Is our mannitol solution negative 0.52? No, it's less than that. It's a smaller depression. It has lowered the freezing point by less than 0.52. Therefore, there are less particles in the solution because the freezing point depression was not as large. Therefore, we have a hypotonic solution. Is everyone okay with that? Since our freezing point depression is less than or smaller than 0.52, it is considered a hypotonic solution. You think you could do the same thing with the sodium chloride equivalent method? Same thing. We're going to come up with the same answer, but let's see if we can do it in a different way. So with the sodium chloride equivalent method, again, we're going to start with the concentration here. And again, going to here, it just comes back around to there. The only thing we got to change about that concentration is instead of expressing it as 36.4 grams per liter, I would prefer to know how many grams per 100 milliliters. And you'll see why here in a minute. So all I got to do is say 36.4 grams per liter is the same as 36.4 grams per 1,000 milliliters. So this essentially is the same as that. Now, to convert it to 100 mils, let's just divide the top and the bottom by 100. By 10, I'm sorry. 36.4 divided by 10 is 3.64 because 1,000 divided by 10 is 100. All I'm doing is converting my concentration per 1,000 down to that of 100. So 3.64 grams per 100 mils is the same as our 36.4. Did I mess with anyone's mind, or is everyone okay with this? That's the same concentration, but now in 100 mils. And you'll see why that's a little more useful here in a minute. Now, this whole thing, once you have your concentration now in grams per 100 mils, let's just look at the E-value. Remember, you had to remember this. What are the units for the E-value? I will provide you no units. I'll just give you the value at 0.18. You know that 0.18 for an E-value means what? 0.18 grams of sodium chloride per gram of drug, in this case per gram of mannitol, okay? This is an important step. You must be able to do that and set up the correct units in the right spot. Because essentially then all we need to do is take our amount, since we already have it per 100, if I just take my amount per 100, multiply it so my grams of mannitol cancel, so 3.64 times the E-value as 0.18 grams of sodium chloride per 1 gram of mannitol, mannitol cancels. Do you see where that's equivalent to 0.66 grams of sodium chloride? Okay? Are you okay with, if I start with 3.64 grams of mannitol, that's equivalent to 0.66 grams of sodium chloride because of the E-value. And I use the E-value so my units canceled correctly. Does that mean there's that much sodium chloride in the mannitol? Is there sodium chloride in mannitol? No, we're saying that the amount of mannitol, the 3.64 grams of mannitol, produces the osmotic forces that would mimic the amount of forces produced by 0.66 grams of sodium chloride. So it's an equivalent amount of sodium chloride. And in the end, the reason I standardize this by 100 is this. You got to know this. Please tell me you know this. What is isotonic sodium chloride concentration? 0.9%, which means 0.9 grams per what? 100 milliliters, which means that since this is the amount per 100 mils, our 0.66 is less than what I would have needed to be isotonic. So clearly, since it's less than that amount of sodium chloride, the solution is hypotonic. So far, so good? A little bit of a review? All right. Now, the last thing we can do with these same sort of formulas is not only evaluate a current tonicity of a solution, but actually say for a solution what concentration would be isotonic. So, okay, we know that concentration, 0.2 molar is no good, it's hypotonic. What is an isotonic concentration in percent, weight per volume, for mannitol? And let's use both the freezing point depression method and the sodium chloride equivalent method. Guess what? It's the same formula. We're just going to solve it differently. So let's start with the freezing point depression method. You'll notice this is set up exactly the same as we did before. The molecular weight in grams per liter divided by the negative 1.86 times the I, which for mannitol was 1. That's the same. Let's set that equal to, now we don't know the concentration. That's what we're solving for. So I put X on the numerator to represent the concentration in what units? Grams per liter, so just keep that in mind, but that's an X concentration over, do we know the freezing point depression we want our solution to have? Yes, we want it to be isotonic. What do isotonic solutions freeze at? Negative 0.52, so that's where the negative 0.52 comes from. Would you agree you can algebra solve for X? So if I do that algebra and solve for X, and I wrote my answer down here, and I kind of just set it out a little funny, you'll see why. I get 51. My number solving for X is 51. Remember, what are the units? Grams per liter. So I expressed it as 51 grams over 1 liter. And I did that because the answer needs to be as a percent. So I can't express the grams per 1,000 milliliters, which is, again, the same thing right here. What I need to do is express it per 100 milliliters. So again, let's just divide the numerator and the denominator by 10. So instead of 51, I get 5.1 for 100 milliliters. So since 5.1 grams per 100 milliliters is by definition its weight, its percent weight per volume, our answer is 5.1. Everyone okay with that? That formula doesn't change. Once you kind of get used to the formula and put in the numbers, you either use it to solve for a concentration given your freezing point, or you can solve, for a freezing point if you're given I don't know if I even said that backwards. All right, let's drive on. Okay, let's do the same thing for the E-value. All right, so same thing. What do we say we need to do with the E-value is you first need to decide what is my target amount of sodium chloride. How much do I need to have to be isotonic? Well, What volume are we doing? We're going to express it as a percent, so let's do it as 100 milliliters. So how many grams of sodium chloride do we need to make 100 mils isotonic? Well, that's by definition the 0.9%. All right, so since this is isotonic and that's the same number, 0.9%, then clearly this is the amount of sodium chloride we need to make 100 milliliters be isotonic. All right, well, there's our E value. Remember, 0.18 means 0.18 grams of sodium chloride per gram of mannitol. So if this is the amount, again, if that's the amount of sodium chloride I need to mimic, and this is my E value set up so that my units cancel. So if I take 0.9 times 1 gram of mannitol over 0.18 grams of sodium chloride, you see where grams of sodium chloride cancel? And I would get grams of mannitol, 5 grams of mannitol. Remember, that's the amount of mannitol per what volume? We set this all up to be the same for the 100 milliliters, so I have 5 grams over 100 mils. That, by definition, is 5% weight per volume. So we came to essentially the same 5% values using both the freezing point depression method and the sodium chloride equivalent method. You don't seem thrilled. This is exciting, man. This is isotonicity. All right, so let's go a little bit further here and now actually solve our problems. And you'll see in some ways it's not as difficult as when we had to count particles because we're going to give you more information than we have up to this point. It's more of a process, so that's what's important. I'm going to go through a bunch of prescriptions doing both methods. You're going to see repetition, doing the same thing over and over again. That's what I need you to learn how to do, is do step 1, 2, and 3 to solve these problems, all right? So let's start with the freezing point depression method. Hopefully you remember by now that we're trying to get to a solution that freezes at negative 0.52. The whole point to any of this is, when we make, for example, I'll just say eye drops or IVs, isn't the point to an eye drop to put some active drug in there? And isn't the concentration of the drug in that solution, the concentration, it needs to be therapeutic? Would you agree? If I'm going to make an atropine eye drop, I need the concentration of atropine in that solution that produces the mydriasis, or the effect on the eye. I'm not worried about isotonicity. The amount of atropine, the amount of active ingredient, is the amount in that solution to produce its therapeutic effect. The problem is that concentration is not usually enough to make the final solution isotonic. So we need to know how much isotonicity or what tonicity comes from the active ingredient at the concentration we have to have, and then add to it whatever we want. We could stick dirt in there to make it isotonic. That's a bad idea. But we could put stuff in there. As long as we put enough stuff that it's isotonic, then my drug is there at the concentration it needs to be, and there's enough other stuff in there so that the solution doesn't create any problems with the eye. Does that make sense? That's what we're trying to accomplish in all of these questions. In this case, we're going to use the freezing point depression to do it. So let's look. The last thing is that the value you're going to need to do that comes straight out of a table. So again, this would be something that would be provided to you on the exam if that's what you're going to be focused on. But for all of our active ingredients, and again, you can calculate this, but in this case, we have a table full of active ingredients that give, this is what's important that you know, a delta TF 1%. What the hell does that mean? Delta means change, right? The capital T with a little f stands for the temperature at which it freezes, the freezing point. So delta TF would be the change in freezing point, and this value is all standardized for a 1% solution. So the delta TF value tells you the essentially reduction, because these are all going to be depression, so the values are all really going down, even though we treat them as a whole number. The reduction in freezing point that occurs when you have a 1% standardized concentration of that product. Okay, that's the delta TF. You're going to see that's the number we're going to use in these calculations. So the way you do it is take your drug. You got to know, to make this product, I have to have this therapeutic concentration of this drug. So let's use the delta TF for that drug to figure out how much of a reduction the drug causes. All right? Once you know how much is caused by your active ingredient, subtract that amount from your target. And what is your target? You just know this, right? Negative 0.52. That minus the amount for my drug tells me the amount of freezing point I still need to get. So pick whatever drug you're going to use or inert substance you're going to use and look up its delta TF value and use that to figure out the amount you need to get the rest of the freezing point depression. Is that okay? So that's the idea between steps 1, 2, and 3. Before we practice this, because we're going to keep going back and forth, let's talk about how you do the same exact thing for the sodium chloride equivalent method. Remember, instead of saying I know instead of saying negative 0.52 for freezing point, for sodium chloride, you know it's 0.9%. That's the amount of sodium chloride I have to have. All right? So what you do in step 1 is you go to the table and you find the E values. Have we used E values already a little bit? We even calculated E values last week. In this case, in these questions, I will provide you the E-value. You just need to use it. So all you do is you take your active ingredient and you use the E-value and say, given this concentration or this amount for my therapeutic use, that amount of drug would mimic this amount of sodium chloride using the E-value. You then decide your target, given whatever volume I'm making, and if it has to be 0.9%, I can figure out how much sodium chloride total I would need. That is my target. Take my target, subtract the sodium chloride equivalent coming from my active ingredient, and what's left, I either add a sodium chloride, or, and that's what's kind of cool about step 4, you can either just do sodium chloride, or you can convert that amount of sodium chloride that you still need to some other drug using its E-value. Okay, and you'll see that going back and forth. So I'd still say you guys like to learn and memorize kind of step by step on how to do it, and that's really helpful. So these 2 slides are important kind of background to be able to apply to the calculations we're going to do here in a minute. Okay? So far so good? I know that doesn't mean anything without practice. So let's practice this. We're going to do those steps. So let's read our first example. And this first example does want to use the freezing point depression method. And what we're trying to do is formulate this prescription. You can kind of see a commercial example down there on the bottom right. But we want to use hydrous dextrose at a concentration of 2.5% weight per volume. Okay? To that, we want to add enough sodium chloride, whatever amount of sodium chloride we need, so that our final volume, our 1,000 milliliters, is isotonic. So we're going to have 1,000 milliliters, that's going to have 2.5% dextrose, and whatever concentration of sodium chloride we need to make the final product isotonic. All right? So far, so good? So we really just need to figure out the amount of sodium chloride. Well, starting with the freezing point depression method, the first thing you need to do is for each of your ingredients, and again, we're going to have both dextrose and sodium chloride, right? Aren't those our 2 ingredients? Let's look up the delta TF 1% values from our table in our textbook, okay? And we see that we have 0.09 for dextrose and 0.58 for sodium chloride. Now that I have those, this is what's really important. I think that the freezing point depression method is the easiest, but you got to be able to set up these proportions. So let's ignore everything. Let's just start right here for now and just look at how to set that up. Delta TF for dextrose of 0.09 means what? Set this proportion up. You get 0.09 degrees Celsius. Oh, I don't want to make that look like a negative sign. Sorry. You get 0.09 degrees Celsius change for every 1% dextrose. Is everyone okay where this number comes from relative to that value? This is extremely important for this method. You need to be able to take the value of a delta TF of 0.09 and say, okay, that means I get 0.09 degrees Celsius change for every 1%. That's why it's called a delta TF 1%. Is everyone okay with that? That's the proportion. Let's set that equal to some unknown reduction. We do not know how much of a decrease in freezing point our dextrose is going to cause, but do we know our concentration of dextrose? What are we going to use in the prescription? 2.5%, so that's where that comes from, all right? So far, do you see where all 3 parts out of a 4-part proportion come from? And can set that up. All you have to do now is solve for x, and solving for x is telling you the degrees of Celsius reduced by that concentration of dextrose. So solving for x, you get 0.225 degrees Celsius. That, and again, it is a negative value. And again, you'll notice in these calculations, I leave the negative off. I treat it as a whole number. But you know it's negative because is it a freezing point elevation or is it a freezing point depression? Depression. So all of these temperatures are going down, are becoming more negative. But to avoid your math errors, some of you, it's easier to deal with them as just whole numbers. All right? So the depression is 0.225 degrees caused by 2.5% of dextrose. So far, so good? Then we start with this value. Where did that value come from? Your mind. You've memorized it, right? What is an isotonic reduction in freezing point depression? 0.52. That's our target. Isotonic solutions freeze at 0.52 degrees. Reduction would be negative, all right? So let's subtract our target from the value we're getting from the dextrose, okay? Target minus the amount from dextrose means I still need to get 0.295 degrees. That's what I don't have. I would need that much to have it be isotonic in the end. All right? So what am I going to use to get the rest of my isotonicity, or my isotonic forces? Sodium chloride. So let's set up the same proportion again. This proportion comes straight from over here. Do you see that? It's set up the same way. My delta TF 1% of 0.58 means 0.58 degrees Celsius for every 1% of sodium chloride. set that equal to, what's different now is I know the amount of decrease I need. That's what I want. I want whatever concentration gives me a 0.295 degrees reduction. Now I put X on the bottom, and X will be the percent concentration that gives me the reduction that I need. Okay? So all I have to do at this point is solve for X. If I cross multiply and do all of that, you find your final answer here is 0.5% sodium chloride. The only trick here is it needs to know how many grams. The question wants grams, and you can now do this however you want. For example, I set up 0.5% basically means 0.5 grams in 100 mils. So if I want to know the amount, how much am I making? What's my total volume? 1,000, right? So if I need 0.5 for 100, then if I multiply the top and the bottom by 10, I need 5 for 1,000. You can solve that however you want. But in the end, would you agree you need 5 grams of sodium chloride per liter, okay, because that would give you essentially a 0.5% solution, and that concentration when added to your 2.5% of dextrose gives you an isotonic solution. Okay? Any questions about that? Please ask, because you're going to see, we're going to do this again and again and again. This core skill, it's not hard once the light bulb comes on, okay? Let's do the same thing. Let's do exactly the same thing now, but use the sodium chloride equivalent method. So we should get the same number, but we're going to do it in a different way. And remember, on the test, do you get to choose? No, that would provide you way too much autonomy. I'm taking your autonomy away on the test and telling you which method to use. So you're going to have to be able to do it either way. So let's do it. We started the same way. Again, while in the freezing point depression method, you needed to know the delta TF. To do the sodium chloride equivalent method, what do you need to know? The E value. So again, you go to your textbook and look up the E value for your products, all right? So in this case, the only E value we really need is for dextrose. I do point out this was a little tricky because dextrose has 2 entries. There is a difference between anhydrous and essentially hydrous. Since the prescription calls for hydrous, which E value are we going to want to use? The one that's for the hydrous, or we're going to want the 0.16. So be careful with that and choose the right E value given your ingredient, all right? Now, we got our E value. What do I do? Well, unlike the freezing point depression where we could leave everything as a percent, here you need to know weight. You need to know grams of your ingredients. So the first thing let's do is let's figure out how many grams of dextrose will be in my product. And I'm going to do that by saying, okay, if I have 1,000 milliliters, that's what I'm making, right? And it's going to be 2.5%. I'm going to take 1,000 milliliters times 2.5 grams of dextrose for every 100 milliliters. That's from the percent. Milliliters cancel, and I get grams. So would you agree? Multiplying that out means my 2.5% of 1,000 mils means I have 25 grams of dextrose. All right? So take that amount of dextrose. So that amount is going to be brought down here, and we're going to multiply it by the E value. Okay? But we have to set up the E value with the right units. I'll still emphasize this. 0.16 means what? 0.16 grams of sodium chloride per gram of dextrose. So you set it up this way so that the units of dextrose cancel. So if I take 25 times 0.16, I end up with units of grams of dextrose, and you do that math, and you get 4 grams. Okay? All we've done at this point, would you agree? Well, this is a good number, but it's not our final number. We know that our 2.5% of dextrose in a liter bag will provide the equivalence of 4 grams of sodium chloride. Is that enough? That's the next question. How much is enough? What is our total? What is our target? You don't know what our target is yet. So our target is to be isotonic, which is 0.9%, which is 0.9 grams per 100 milliliters. Just multiply the top and the bottom by 10. That's the same as 9 grams per 1,000 mils. I will tell you, both of these numbers are good things to memorize. It just makes life a little easier. Can you tell me emotionally now that you see that those are the same thing? That 0.9% is 0.9 grams per 100 mils, and that is the same as 9 grams per liter. Just make sure you can do that. Okay? Since now we're making a liter, would you agree our target is 9 grams? So let's start with our target of 9 grams, subtract the 4 grams. Now there's too many lines here. This is not helpful. I apologize. Just realize, take our target of 9 grams, subtract what we're getting from our dextrose, which we said was 4 grams. The difference is how much? 5 grams. Wham. Isn't that what we got in the previous one too? Amazing. It's magic. Mathematical magic. Are you okay? We just did the same darn thing twice, okay, in 2 different methods. All right, ready to move on? Ready just to be done? Don't answer that. All right, let's go on to the next prescription, man. So we made an IV product. Let's move on to an eye drop, an ophthalmic solution. Then they also have to be sterile and isotonic, not to cause problems in the eye. So in this case, our prescription calls for homatropine hydrobromide, 1.5% weight per volume solution. We want to make it isotonic using, it's not sodium chloride. What are we using? Boric acid. It's a different thing, okay? We're going to use it just like sodium chloride, but it's a different thing, all right? We're going to use boric acid for the tonicity adjusting. And this is where it gets important now. Make sure you're to a final volume of what? 20 milliliters. So we want to make 20 milliliters isotonic that has 1.5% weight per volume of homatropine hydrobromide. Now, you guys should know what homatropine hydrobromide is, right? Have you guys talked about that yet? All of your autonomic-y, nervous-y, system-y stuff, right? It's a anticholinergic used for mydriasis to dilate the eye when they want to do procedures and look inside your eye. So that's what we're trying to make. Which one do you want to do first, freezing point or sodium chloride equivalent method? Once again, you don't get a choice. We're going to do freezing point depression method, all right? So freezing point depression method, that's the one we're doing here. What do we start with? We go to the table, we look up the delta TF 1% values. Man, it's the same thing, different numbers. Homatropine has a 0.11 in the boric acid. Why do we need to look up boric acid? That's the other thing we're going to add to be able to make up the difference. So we need to know the delta TF for the boric acid. We have both of those numbers. Easy breezy. What was step one? To figure out the freezing point depression caused by my therapeutic agent. Which of those two are my therapeutic agent? The homatropine, right? So let's start with the homatropine. So let's take this value from the table, come over here and re-express it. So 0.11 means 0.11 degrees Celsius for every 1% concentration of my homatropine. Let's set that equal to some unknown reduction in freezing point, divided by how much are we going to have in there? Remember, the whole point is to make a solution that has a therapeutic concentration of 1.5% homatropine. So when I have that therapeutic concentration, how much will it reduce my freezing point? Okay? Solve for X, and you would have a reduction of 0.165 degrees. Yay. It's not enough, though, right? Because what is our target that you've memorized? 0.52, so let's take our target of 0.52, subtract this number, so that's where that number comes from. That's the amount from the homatropine, so my target minus the amount from my drug gives me 0.355 degrees Celsius that I still need to get. All right? Do you see why that's still left over? My homatropine doesn't give me enough to be isotonic. The difference is between what homatropine does and what I need to be is 0.355 degrees. What am I going to use to get that reduction? The boric acid. So now let's go back to my boric acid and do the same process and pull its delta TF 1% over and re-express it as 0.29 degrees Celsius for a 1% concentration. Set that equal to, but now I know the degrees I want. I want it to be reduced exactly 0.355 over X, and X will be the percent concentration that would reduce that freezing point by that 0.355. Solve for X, and you get 1.2, but here's important. What are the units on this? I worry about some of you. Remember, the units, when you solve for this, X represented the concentration is a percent. So we need 1.2%. How many mils are we making, though? We're not making 100 mils. We're making how many mils? 20 mils. So remember, the last step, once you know your concentration, is to do this however you like to do it. But if you need 1.2 grams per 100 milliliters from the concentration, you can set that equal to X over 20 mils. And just figure the weight in grams of the amount of boric acid you need for only 20 grams given that concentration. Solve for that X, and you get 0.25 grams of boric acid. So in the end, that's the amount of boric acid that needs to be added to the homatropine so that the final solution is isotonic. Remember, they're additive. The two things added together give you the total that you need. So far, so good? All right, same darn thing, all right? E values, let's do sodium chloride equivalent. Go to the table, look up the values. Instead of delta TFs, they're E values. Do you see the two E values that we have there for our ingredients, both boric acid and homatropine? Let's start again with the homatropine. Again, we can't use it in percent. The 1.5% doesn't help me. I need the weight of the homatropine, all right? So let's take and figure out how much homatropine will be in there. Remember, it's a 20 ml solution at that concentration, so all of that's what I bring over here and take my 20 mils times its concentration expressed as 1.5 grams per 100 mils, since that's a 1.5% weight per volume. 20 times 1.5 divided by 100, milliliters cancel, and I get my total weight of homatropine that I'll need is 0.3 grams of homatropine. Everyone okay with that? So that's how much is going to be in my solution because that's how much is therapeutic. Now I'm going to take that same number and convert that to its equivalent amount of sodium chloride. So 0.3 grams of homatropine is what's in there. It has the same osmotic forces as how much sodium chloride. How are we going to convert from homatropine to sodium chloride? We're going to use the E value. So let's go over here to the E value for the homatropine, 0.17. Let's set that up with the right units. 0.17 means 0.17 grams of sodium chloride per gram of drug, in this case homatropine. This way, if I multiply these two together, homatropine cancels, and I'm in grams of sodium chloride. So what is 0.3 times 0.17? It's 0.05, and remember that's in grams of sodium chloride. That's how much sodium chloride my homatropine mimics. All right? Is that enough? How much sodium chloride do we need? Well, that's the next step, is to set out my target. What is my target? My target is 0.9%, which is 0.9 grams per how many mils? 100 milliliters. But I'm not making 100 mils. How many am I making? I'm making 20. So let's set up this proportion and solve for x. All right? So 0.9 times 20 divided by 100 gives you a total weight of sodium chloride for only 20 milliliters of 0.18 grams. Is everyone okay with that? I don't want to freak anyone out here. 0.9%, 0.9 grams in 100 mils is the same as only having 0.18 grams if you're only making 20 mils. So that's the amount of sodium chloride I need, is the amount of sodium chloride to make 20 milliliters isotonic. Okay, because now that's my target. So that's what I'm going to bring over here as my target. Since that's how much I need for my 20 mils, let's subtract. What did I say I got from my homatropine? I got 0.05. So if I subtract those two, the difference I still need to make 20 milliliters isotonic is the difference of 0.13 grams. Okay, I just subtracted those two. That's the amount that I want to need. Yay, but I'm not using sodium chloride. What am I using to get it? Boric acid. So let's take the amount of sodium chloride I need and now apply boric acid's E value down here like this. 0.52 grams of sodium chloride per gram of boric acid. Let's set it up as 1 gram of boric acid over 0.52 so that those units cancel. So 0.13 basically divided by 0.52 gives you a total weight of boric acid of 0.25 grams. Is that the answer we got before with the freezing point depression method? Yes, we did the same thing in 2 different ways. All right, let's do it again because you guys are good and love doing this. It is kind of cool. Is it getting a little repetition beyond me and my speaking getting repetitious? Is the procedure, are you starting to see the steps a little bit? The whole point of this is step 1, step 2, step 3. So as you're watching me do this, make sure you see, well, he's doing this, and now he's doing this, and now he's doing that. So we've done this before, so let's see if we can do it a little quicker. It says, for the snafazoline, which is basically a red eye remover, it's a vasoconstrictor, so it's what gets rid of the red eye. So naphthalene hydrochloride, 1%, with enough sodium chloride to make what volume isotonic? This is important, guys. Make sure as you're doing these calculations, don't forget to look at the final volume because it will determine how much stuff you need to have in there, right? So it's about concentration. So make sure you pay attention to that as well. 1% naphthalene using sodium chloride, make 30 mils isotonic. Let's start with the freezing point depression method. Let's look up the 2 ingredients. We got naphthalene at 0.16 delta TF and sodium chloride again at 0.58, straight out of the textbook. What do we do first? Let's start with our active ingredient. It's the same procedure, man. So let's take this delta TF for the drug, come over here, set it up as 0.16 degrees Celsius over 1% naphthalene equal to some unknown reduction in concentration over, what's our concentration therapeutically? 1%. Oh, you're welcome. See, that's a little bit easy, right? So solve for that, and you see you get a 0.16 reduction in temperature and freezing point because you're using the 1% concentration. Our target is 0.52. Subtracting this number here, we get 0.36 left to do, all right? What are we using to get that reduction, that additional reduction? We're using sodium chloride, man. So let's pull that back over, set up its delta TF as 0.58 degrees over 1%, equal to what we want, which is 0.36 degrees over x. We solve and we get a percentage. So we're getting 0.26% sodium chloride that we still need to obtain. Okay? However, the question wants grams of sodium chloride. So all we need to do is convert that into the amount for our 30 mils. Okay? That's per 100 mils. So again, that concentration is 0.26 grams per 100 mils. How many grams would we need? And that's why I'm trying to remind you, this isn't important always for the last step. The amount we actually want is only 30 mils. So 0.26% is 0.26 grams per 100 mils. Set that equal to some unknown amount per 30 mils. Then you're finding the weight of sodium chloride you need for the volume you're making, which is 0.19 grams of sodium chloride. Okay? Can we do it again? Let's do it again. All right, so for sodium chloride equivalent method, we look up the E value. So again, there's the E value that we need for our active ingredient. So let's do it. Remember, the problem with the the sodium chloride equivalent method is that it doesn't help me to have my concentration as a percent. So let's start by converting this 1% of 30 milliliters, combine those and bring those over here and calculate the actual weight of naphthalene. So take 30 milliliters times its concentration of 1% as 1 gram per 100 milliliters. Milliliters cancel. And that basically says in that amount, at that concentration, I would have 0.3 grams of naphthalene. Okay? So that's the amount that I bring down and use my E value now to convert over to sodium chloride. So 0.27 grams of sodium chloride per gram of drug. This way, if I multiply it like this, my grams of drug cancel, and 0.3 times 0.27 gives you 0.08 grams of what? Sodium chloride. That's the amount of sodium chloride our naphthalene mimics. Let's go back and figure out our target. Our target is 0.9%, but since we're only making 30 milliliters, we don't need 0.9 grams. How much do we need? So take 0.9 times 30 divided by 100, essentially solve for X, and you see our target sodium chloride is 0.27 grams. Why is it not 0.9? Because we're not making 100 mils, we're making 30 mils. So we proportioned the amount of sodium chloride we need. So that's our target. That's what I'm going to put down here, and I'm going to subtract the amount that I got from my naphthalene, my active ingredient, which was the 0.08. So the 0.27 minus the 0.08 means you still need 0.19 grams of sodium chloride. All right. This is, you know what to do. So the last question, because I know you'd be bored by now, is kind of a mini review. So we'll eventually get to the isotonicity calculation at the end, but let's test your mathematical prowess up to this point by asking a couple of other kind of cool questions along the way. So let's make a chromoline sodium eye drop. All right, so is this commercially available? Have you guys heard of chromoline sodium? Okay, it's essentially used for allergies, eye allergies. It's a mast cell stabilizer, so it prevents histamine release. It's not an antihistamine. It keeps the histamine from coming out to begin with. So use it over enough time, then you don't respond to those allergens. You don't get the red, itchy eyes. So that's what we're making. Prescription calls for 5% chromium, which is our active ingredient. We also need benzalkonium chloride at 0.005%. Be careful with your numbers when you do these small numbers. What the heck's benzalkonium chloride for? I think we've talked about this before. Do you know what it's used for? It's really low amount because it's a preservative. We're using it to keep any sort of bacteria from growing in our eye drops. So again, a small amount of benzalkonium chloride to prevent bacteria from growing in our formulation. And then glycerin. Why are we adding glycerin? That's our tonicity adjuster. Beyond the amounts we need for the benzalkonium chloride and the chromoline, whatever is left to make the final product isotonic, we're going to use glycerin. Can anyone tell me why glycerin is kind of an advantage in this case? It comes as a liquid, so we'll be able to measure the volume that we need to use in the eye drop instead of having to weigh out a solid, okay? And then as much water as we need, and this is important to conclude that we're making everything in the end, so our final concentration is in 15 milliliters, all right? Now, first question, how many milligrams of chromoline sodium should be used to fill this prescription? Please tell me this is easy. Do you have a volume that we're trying to prepare? What's our volume? 15 mils. Do we have a concentration? 5%. Ooh, this is the percenty thing. 5% weight per volume would be how much? 5 grams per 100 mils, right? So that's, again, you need to be good with expressing percentages in terms of units and weights. So again, this is easy, hopefully. Let's take the volume we're trying to produce, the 15 milliliters. Let's multiply it by its concentration. We said 5%, that's 5 grams per 100 mils. So if I multiply it like this, my milliliters cancel, and now I'm in grams of chromoline. However, it wanted to know milligrams, so I'm just going to multiply that by the fact that there's 1,000 milligrams per gram. That way my grams cancel, and your final units would be in milligrams. If you do that multiplication all the way across, you should get the number of 750, and it would be milligrams of chromoline. Okay? Easy? Little review, concentrations. We'll never stop doing concentration stuff. All right, this is kind of an interesting question. That's the total amount I'm in there, but how much, every time I put a drop in my eye, how much drug am I getting? How many milligrams, if this is a 5% solution, when I put a drop in my eye, how much drug am I getting? Okay, well, there's two things that affect that. It's the size of a drop, and not all droppers are the same, so there's no universal mils per drop, so it has to be calibrated for the dropper. We're saying in this case, this little dropper that we're using drops 50 microliters per drop, so I had to provide that to you. There's no universal number for that. So in this dropper, though, every drop has 50 microliters, and we know it's a 5% concentration. So each drop will contain a certain amount of drug. But have you guys ever used an eye drop and you put it in there? Does it all stay there, or does some of it get wiped away or washed away pretty quick? Okay, the eye can only hold so much. And usually you want a drop to be larger than that amount, so there's excess. That's why there usually is leakage. It provides more than enough drug. And in this case, we're saying the eye will only hold about 10 out of those 50 microliters. So the question is asking how much drug will be in each drop, and then the second question, how much drug will actually stay on the eye, given the fact that only 10 microliters stays there. Okay? So where do we start? Would you agree the amount of drug that gets to the eye will depend on the amount or the size of the drop? The larger the drop, the greater the drug. So let's start with the drop, man. So to answer the question about how much drug is in each drop, let's start with a drop and convert it from drops to a volume. So if I multiply each drop by the fact that we were told there was 50 microliters per drop, then drops cancel, and I'm in microliters, all right? The problem is my concentration is in milliliters, so let's get rid of microliters. That's just weird. So let's multiply that by the fact that I know in every 1 milliliter, there's 1,000 microliters. That way microliters cancel, and now I'm in a unit I'm comfortable with. I'm in milliliters. Plus, I can express my concentration as 5%, meaning 5 grams per 100 mils. So if I multiply it by that, then milliliters will cancel. And I'm now in grams. But the question wanted to know milligrams. So all I got to do to convert milligrams to grams is multiply it by 1,000. That way grams cancel. Do the math all the way across. And would you agree a 50 microliter drop that has 5% concentration has 2.5 milligrams? That's your final answer. But we said not all of that drop is going to stay into the eye. So now you can solve this a couple of different ways. You know me, I like to do it the long way with all my units. So if you had no other clue on how to handle this, let's just start with, okay, well, it's a 50 microliter drop, but in the end, I want to know the amount that's going to stay in the eye, and the only volume that stays in the eye is 10 microliters. So let's start with 10 microliters, that's what's in the eye, convert it to milliliters by multiplying by 1 mil over 1,000 microliters, so that microliters cancel. Do the same process now, times the concentration, times 5 grams per 100 mils, so the mils cancel. Convert grams to milligrams, and again, these cancel, and you end up with your total amount of 0.5 milligrams. Could you have done that an easier way? That each drop is how much larger than the amount that stays in the eye? What is 50 divided by 10? It's 5 times the amount. So if you only divided the amount by 5, what is 2.5 divided by 5? 0.5. So again, you're getting a fifth of what you're adding. So if you just had divided the 2.5 by 5, that would have done it as well. But you don't have to be able to see that. You can do it the long way as well. Okay? All right, so the next part of it, it says how many milligrams of benzalkonium chloride, and how many milliliters of a 1 to 750 ratio strength in weight per volume would be needed to fill this prescription. Oh my gosh, do you remember the ratio strength thing? Remember, you're good on concentrations, you're staying calm, it's not a big deal. Pretty straightforward. We start the same place. Let's take the volume that we're compounding, which is 15 milliliters, times its concentration in the prescription, which was 0.005%. That's 0.5 grams per 100 milliliters, so that milliliters cancel. I'm now in grams. Convert that to milligrams by multiplying by 1,000. And essentially, I need 0.75 milligrams of benzalkonium chloride in my 15 milliliters to give it the right percent. Okay? So the next step is certainly how many milliliters of my solution do I need to get that? All right? So this is the amount I need. I'm just bringing it down to here. My first step, though, is to convert from milligrams back to grams. And you'll see why here in a minute. I can't deal with milligrams. So 0.75 divided by 1,000 gives me the weight in grams. And I did that because here's my concentration. And this is what I mean by hopefully I can't mess with you in concentration. You know a ratio strength, 1 to whatever, is in weight per volume, the units of grams per milliliter. It's not standardized. It's not a percent. A percent is how many milliliters? A percent is 100 A ratio strength isn't a percent. It's whatever number you have. So it's 1 gram for 750 milliliters. And just set it up so that the units cancel. So I multiply by 750 milliliters over 1 gram. Now when I multiply across, my final unit would be in milliliters, and the math would be 0.563 milliliters of that 1 to 750 concentration solution. Is everyone okay with that, and where that came from? Is this all review, I hope, a little bit? Remember some of this stuff. This isn't anything new, because we're going to finish up, and I promise this is the last question before you're free. We haven't done the isotonicity thing yet, and this is a good example. This one's a little more complicated, okay? Only in the sense that, would you agree, do we have 1 active ingredient or 2 active ingredients? 2. We have both the chromalin and the benzalkonium chloride. Okay, so it doesn't change anything other than the fact we have to add all of that up. We can't ignore any of it. This question basically is how much glycerin do I need to add? And the amount of glycerin is the amount to make the final product isotonic, assuming both of our current ingredients. The nice thing is I'm only going to have you guys do the E method here, okay, so the sodium chloride equivalent. What's the first step for the sodium chloride equivalent? Go to the book, man, and let's look up the values. So I have values for E values for both the benzalkonium chloride and the chromalin sodium and the glycerin. We need E values for all of our ingredients. All right? The first step was to, and again, I'm going to separate these. I combined a couple of steps, but that is for the chromalin. This is for the benzalkonium chloride, so let's not get confused. Let's start with one thing here. Let's start with the chromalin, sorry. 15 milliliters, which is the volume we're doing, times its concentration. We said we wanted it to be 5%. So 15 mils times 5%, 5 grams over 100 mils, gives me the grams of chromalin. Okay? I'm now combining a step. Because can we not relatively quickly convert from grams of chromium to grams of sodium chloride using the E value? Right? What did we say the E value of 0.11 would mean? 0.11 grams of sodium chloride per gram of drug. So now my chromalin cancels, and I'm in grams of sodium chloride. So if you just multiply that straight across, you would get the amount of sodium chloride equivalent produced by the required amount of chromalin sodium to be 0.083 grams. Is everyone okay with that? All I did was first convert from my volume using my concentration to my weight of chromalin, and then use my E value to convert from grams of chromalin to grams of sodium chloride. Because now I'm going to do that same exact thing for the benzalkonium chloride. So I won't repeat all of this. They're my 15 mils times its concentration. But again, we look at it has a different E value. So I got to come over here and say its E value is 0.16 or 0.16 grams of sodium chloride per gram of benzalkonium chloride. That's why my benzalkonium chloride cancel. And my final answer for this benzalkonium chloride is small, but it's 0.0001 grams of sodium chloride. Everyone okay with that? We just did it twice. 2 ingredients, we do the same thing. Once for one first ingredient, again for the second ingredient. Next, what was this step? The target. How much sodium chloride do we need total? That's not going to change. We need 0.9%. Okay, which is 0.9 grams per 100 mils, but I'll remind you, we're not making 100 mils, we're only making 15, so how much sodium chloride do I need for 15 milliliters? Solve for X, and you'll see that for 15 milliliters, I only need 0.135 grams of sodium chloride. That's the target. That's what I need, all right? So from that target, let's subtract each ingredient. From the total that I want, let's subtract the chromalin sodium, which we calculated to be 0.083, and also subtract the amount from the benzalkonium chloride. So from 0.135, I subtract 0.083 and 0.0001 grams, and what's left is the amount of sodium chloride I still need. That's all the same up to this point, kinda, with the 2 ingredients. Everyone okay? Fine. This is important given our experience with specific gravity. It was kind of cool because here's the deal. That's the amount of sodium chloride I need. But I'm not using sodium chloride, I'm using glycerin. So let's use the E value for glycerin to come over here and convert from grams of sodium chloride into grams of glycerin. So again, I'm going to multiply by the fact that for the E value, you get 1 gram of glycerin for 0.34 grams of sodium chloride so that those units cancel. The last little trick is I'm in the weight of the glycerin, but I want to be able to measure glycerin by volume. So what do I need to have? The specific gravity or the density, and I was given that up here. So if I apply that at this last step down here, I can multiply by the fact that in every 1 milliliter, there would be 1.25 grams grams cancel, and now when I multiply across, my final units will be in milliliters. And if you do that math, you will get 0.12 milliliters of glycerin.